Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 5, Lesson 3. Please remember that Unit 5 is about magnetism. And yes, magnets are fun things with a north end and a south end, but the big deal in magnetism is that a moving charged particle creates around it a magnetic field. And that magnetic field will exert forces on other moving charged particles. So remember, if this is the particle that's creating the magnetic field, that magnetic field will not push on this particle. This particle creates a magnetic field. And the magnetic field created by this moving charged particle can exert forces on other moving charged particles. Just like if we were out in space and we had a planet. This planet creates around itself a gravitational field. Well, this gravitational field is not going to push this planet, but this gravitational field will exert forces on other matter. So the beauty of magnetism is that moving charged particles create a field. What kind of field? A magnetic field. And then this moving charged particle creates a magnetic field. That magnetic field, in turn, will exert forces on other moving charged particles. We represent a magnetic field with the letter capital B. We represent a magnetic force, since it's a force, with the letter F, with a little sub capital B. So this is a magnetic field. This is a magnetic force. All forces have the unit newtons, which is the same as a kilogram times meters per second squared. Magnetic fields have the unit, here we go, newtons per coulomb meter per second. Because the field pushes with a certain number of newtons per charge and per speed. So again, the unit for all forces is newtons. That's easy. The unit for magnetic field, newtons per coulomb meter per second. Okay, so what we're getting, so that was just our little review, introduction. We're talking about magnetism. What I want to talk about today is 4 different equations that we can use to determine the strength of magnetic fields that are created, and therefore the strength of the forces that those fields exert. So there's going to be 4 equations that we talk about. And here they are. So here are the 4 equations for today. And I just want to go through, all we're going to do today is I'm going to go through the 4 equations. I'm going to tell you what situation the equation is describing. And then I'm going to show you a diagram and tell you what all of the different letters mean. So how you would use the equation. So let's start with this first equation. This first equation it's about this. I said a moving charged particle creates a field. So that's what's going on here. A moving charged particle creates a field. Now, usually, when charged particles are moving around in physics class, we don't just have them flying through space. We have those moving charged particles inside a wire. And what do we call those moving charged particles? We call those moving charged particles a current inside the wire. So that's what's going on here in this first equation. If I have a wire carrying a current I, it will create a magnetic field around that wire. So that looks like this. Here's the wire, and there's a current inside it, I. And then B is describing the magnetic field surrounding this wire. Now, this equation is very important. It is called Ampere's law. Ampere's law. You may remember that the unit for current is the ampere. Current is the number of coulombs per second, but a coulomb per second is abbreviated using this dude's last name. So you could look up Ampere, and I bet you he did a lot of work with electricity and current and stuff. Anyway, so this equation is called Ampere's law. And you will, if you take physics in college, you will hear college professors talk about Ampere's law. This is it. Now, when we have a wire with current, let me change. That's not it. I want to change what you see. I'm going to stop sharing my screen. There, now you see me. I'm bigger. So if we have a wire with current traveling through it in the direction of my thumb, we use our thumb of our right hand. Use your thumb of your right hand to represent the direction the current is flowing. The field created around the wire points the direction indicated by your fingers. So the magnetic field above the wire is pointing toward you guys. The magnetic field below the wire is pointed toward me. I have to keep my thumb pointing in this direction. See how my thumb is always pointed that direction? But when my fingers are above the wire, up here, the field points toward y'all. When my fingers are down here below the wire, the field points toward me. When I'm talking about between you and me, there, the field points down. Between me and the wire, the field points up. See, my fingers are pointing up. So your fingers indicate that direction. Let's see how I could show that on my piece of paper over here. Share screen. There we go. So now we're back to seeing the piece of paper here. If I have a wire and the current is going this way, then I run my finger. Oh no, my thumb is pointing the wrong direction. So this way, do you see how my fingers are pointing into the page down here? But then when I move my fingers up here, my fingers are pointing out of the page. So the field created points out of the page up there and into the page down there. Into the page, out of the page. The field points in different directions in different places. And then how far we are away, does it make sense to you that the field created by this wire gets weaker as we move farther away? That is what this letter R is. In fact, it's interesting that 2 pi r is the circumference of a circle. We'll see a circle in a minute, but this is R. So how strong is the magnetic field right here? It's equal to mu naught times I divided by 2 pi times this distance. If I go twice as far away, the field is half as strong. If I go half as far away, the field is twice as strong. What if the wire is going this way? The wire is pointing toward you. So if this represents the wire and the current is coming right at you, so the current's going this way. Well, then I'm going to have my thumb point in the direction of the wire. And you see that my fingers point in different directions in different places. So the field, magnetic field, points that way there. And it points that way there. And it points that way there. And it points that way there. And in fact, it points that way there. And it points that way there. And it points that way there, and it points that way there. Use your right hand, have your thumb point in the direction of the current, and see that those are the directions that the field points. This is not how we usually draw it. What we usually draw is this. We draw a circle like that, and we say that's the magnetic field. Maybe we could draw multiple circles like that. So the field points to the left above the wire. The field points to the right below the wire. The field points toward the top of the page to the right of the wire. The field points toward the bottom of the page to the left of the wire. What I would not say is the field goes in a circle. The field isn't going anywhere. The field points in different directions at different locations. Oh, look, there's a circle, and the circumference of each of those circles is 2 pi r. This distance is r. So the field is weaker here, stronger here, stronger here. All right, that is what Ampere's law is, and that is what all the letters in Ampere's law mean. I'm going to peek at how I'm doing on time. Okay, good. This next equation has two currents, because the next equation is about what happens when I have two wires that are each carrying current. This one's carrying a current I1. This one's carrying a current I2. And it turns out that when I have two wires that are parallel and they're carrying current, they exert forces on each other. This F here, represents how hard this one pushes this one. And you're like, well, doesn't this one also push this one? Yes. So if this one pushes this one, does this one push this one? Yes, Newton's third law. So this F is either how hard one pushes two, or it's how hard two pushes one. Either way. And it might make sense to you that more current would mean a stronger force, and less current in either wire would be less force. D represents the separation between the wires. And it makes sense that D is in the denominator, right? If they're farther apart from each other, they're not going to push as hard. If they're closer together, they're probably going to push each other harder. So that's why there is a D there. And then this L represents the length of the wires. Longer, each little segment here pushes each little segment here. This segment pushes this segment. This segment pushes this segment. So if there's a longer wire, there are more segments to push on each other. So that makes sense. I would have written this equation. I would have scribbled out the L there, and I would have put it there in the numerator. So longer wires, more force. The way it is in your book, it put the L over there. Of course, that's equivalent algebraically, and it's called force per unit length. Make sense? So that's how you use that equation. But there's something much more fun. We talked about this one exerts a force on this one, but we didn't talk about what direction this one pushes this one, or what direction this one pushes this one. So let's think about it. I'm going to make this top wire purple, just for fun. Let's think about the field, the magnetic field created by this purple wire, the purple wire. What direction is the field created by the purple wire? Well, as we learned in Ampere's law, it's in different directions at different locations. So what I care about is what direction is the magnetic field here, because it's the magnetic field here that's going to push this wire. So I'm going to make my right thumb point that direction, and I see that at the location of this wire, the magnetic field points into the page. So this wire is purple, and this magnetic field is purple because it's created by this wire. Now I want to know, if I've got current flowing in this wire, what direction does this purple field push this current carrying wire? So remember our VBF right-hand rule. So I've got V, because this is the direction of the current, BF. That means that the force exerted on this black wire by the purple wire is this way. And I'm going to call that F sub B. These X's are B, the magnetic field. This arrow is F sub B. Well, that's interesting. So this wire pushes this wire up. Now we could do all of the same right-hand rule stuff. We could take this black wire here and say, what direction is the field that it creates at this location? And then what direction does that field push these moving charged particles? Feel free to do that on your own time, but I'm going to run out of time, so I'm not going to do it. I'm going to use Newton's third law. If wire 1 pushes wire 2 up, what direction does wire 2 push wire 1? Because of Newton's third law. Remember Newton's third law? A pushes B that way. B pushes A the opposite of that way. So if this wire pushes this wire up, that means this wire pushes this wire down. And since they are pushing each other, since this one pushes this one toward this one, and this one pushes this one toward this one, we call that attraction. Now, does that mean that all current carrying wires attract each other? Let's draw it one more way. Let's say we have a green wire with current going one way, and we have a purple wire. What if the currents aren't going in the same direction? Well, let's see. This green wire creates a field here that's into the page. All right, into the page. So now let's see what direction the force is that's exerted by this green field on this purple wire. V, B, F. Oh, so this was B, the magnetic field, but that field pushes the wire this way, F sub B. That's the opposite direction as we got up here. Why is that opposite? Because here, the current in the bottom wire also traveled to the right, just like the current in the top wire. But here, the current in the bottom wire is traveling to the left, not like in the top wire. If top wire pushes bottom wire down, then bottom wire pushes top wire up. And we're going to call that repulsion. So there we have it. When we have two wires pushing on each other, when we have two parallel wires, both with current, if the current's in the same direction, the wires attract each other. And if the current is in opposite directions, the wires repel each other. How hard do they attract or repel each other? The force per unit length is mu naught I1, I2 over 2 pi d, where I1 and I2 are the two currents, and d is how far apart they are. You could summarize this by saying these two have current in the same direction, so likes attract. And these two wires have currents in opposite directions, so opposites repel. That's a nice summary. Likes attract and opposites repel. Oops, that's just one L. R-E-P-E-L, that's one L because I know how to spell. Likes attract and opposites repel. Wonderful. All right, that is our first equation and our second equation. Now let's look at our third equation. This equation is about a loop of wire, and it's about the magnetic field inside a loop of wire. So if I have a loop of wire like this, and the wire has a current in it, I, and the loop has a radius, R, there is a magnetic field inside the loop. And this is the strength of the magnetic field. If there's just one loop of wire, B is mu naught I over 2R. If it goes around a few, several times, each one adds mu naught I over 2r again. So if I have 2 loops, it's mu naught I over 2r times 2. If I have 1, 2, 3 loops, it's mu naught I over 2r times 3. So n is the number of coils, number of loops, number of times the wire goes around the loop. And the magnetic field is in here. Let's think about what direction the magnetic field points in here. So again, we're going to use our right hand rule. Take your thumb on your right hand and make your thumb go in a circle around there. And you can't have it go all the way around, but have your thumb go in a circle around there. And you'll see as you do that, that your fingers tend to be on the outside of the circle and they point into the page. But with a little bit of manipulation, you can have your thumb go around like this with your fingers on the inside of the circle. And if you do that with your fingers on the inside of the circle, you'll see that they're always pointing out of the page. So the magnetic field in this situation is going to be out of the page. You could memorize that. Counterclockwise current, the magnetic field points out of the page. Clockwise current, the field points into the page. But I wouldn't memorize that. In fact, I've been doing this for decades and I don't have that memorized. I always just use my right hand rule and I run my thumb around there. In this direction, when my fingers are on the inside, they point out of the page. So this equation is for a loop of wire to find the magnetic field inside. Now, this final equation, oh, thank goodness, we're going to finish just barely in time. This final equation is for a solenoid. So this is just for a loop of wire. This is for a solenoid. What is a solenoid? A solenoid is very much like a loop of wire, but instead of it being, a loop of wire like this, where all the coils are pretty much right on top of each other, a solenoid takes the coils and spreads them out like the coils of a spring. So like this. Well, not like this. I mean, if I turn this on its side, it might look like this. But what if I spread those coils out so that it looks like this? I'm going to hit pause for just a second. I love it when friends stop by. I think I was just about to draw the solenoid. So it looks like this. The coils are stretched out over space, kind of like if you have a slinky and you stretch it out. So that's what this equation right here is. B equals mu naught Ni. B equals mu naught Ni. And so it's the strength of the magnetic field inside. So I'm going to try to draw the arrows. This is the magnetic field inside the solenoid. And if I have more current flowing through the wires, I have a stronger field. If I have less current, I have a less strong field. This mu naught appeared in a lot of equations, the permittivity of free space. I know I showed you the numerical value before, but I'm just going to show it to you again to be complete. I'm sorry, I said permittivity. I meant permeability. 1.26 times 10 to the minus 6th. I'm going to make sure I got it right. Yes, and it's called the permeability of free space. Of course, if there's no current, there's no field. So this is the kind of thing that you could turn on and turn off. If maybe, we somehow connected these ends and put a battery in here. and we had a little switch, we could, hook up or unhook the battery, and the current would either be here or not. And this magnetic field would either be here or not. And in that case, we would call this an electromagnet. Turn the current on, you've got a strong magnet. Turn it off, you've got no magnet. So you can make a magnetic field appear or disappear, almost like magic. That's super cool. The other thing, and it's the last thing I have time for, is I want to point out that when I was talking about the number of turns, I used a capital N here. So what's this little n? This little n is not the number of turns. Little n is the number of turns. And then my solenoid has a length. So little n is big N over L. This is the number, it's called the number of turns per unit length. So more turns per each centimeter makes N bigger. So anyway, the total number of turns and the length both matter. Little n is the turns per length. Capital N is just the number of turns. And it's a big deal because you'll get the wrong unit. Capital N, the number of turns, is dimensionless. Since length has the unit meter, little n has the unit m to the minus 1, right? 1 over meters, or m to the minus 1. N is dimensionless. Little n has the unit 1 over meters, or m to the minus 1. And we want to be accurate and precise when we talk about those things. I think that's all I have for you today. I hope you've enjoyed these 4 equations. The one that probably turns out to be talked about the most in physics is Ampere's law. And the one that's maybe the most fun is an electromagnet, because it's super cool to turn a switch. There's a magnet. Turn the switch the other way. There's no magnet. Super fun. Have a wonderful day. Be careful out there, and don't break the laws of physics.